Welcome to part 2 of our tyre markings training. In this video, we will learn how to read and interpret the information printed on a tyre sidewall and understand what those numbers, letters and symbols tell us about the tyre. For engineers, this is important because tyre markings influence load capacity, speed capability, mobility, gearing calculations, suspension design and overall safety. By the end of this session, you should be able to look at a tyre marking and understand the key engineering information it provides before selecting or integrating that tyre into a vehicle. Tyre markings may look like a simple combination of numbers, letters, and symbols, but they contain critical engineering information about the tyre. Understanding tyre markings is important because they directly influence load capacity, vehicle speed, mobility, gearing calculations, and suspension design. For example, the tyre size marking tells us the tyre width, aspect ratio, and rim diameter. These dimensions affect the overall tyre diameter, ground clearance, rolling radius, and vehicle speed calculations. The load index indicates how much weight each tyre can safely carry, while the speed rating defines the maximum safe operating speed. Other markings provide information about tyre construction, ply rating, load range, manufacturing date, rotation direction, and whether the tyre is tubed or tubeless. For a vehicle, selecting a tyre only by its physical size is not enough. Engineers must correctly interpret all tyre markings to ensure safe operation, proper vehicle performance, and compatibility with the wheel, suspension, and drivetrain. Welcome to part 2 of our tyre training program, where we will focus on tyre markings. In this video, we will first understand tyre diameter and width, and how these dimensions influence vehicle packaging, ground clearance, and rolling radius. Next, we will look at construction-type markings, including radial and bias ply tyres. We will then explain the load index and speed rating, which define how much weight a tyre can carry and the maximum speed at which it can operate safely. After that, we will study the DOT code, which provides manufacturing and tyre age information. Finally, we will cover specialized markings, particularly M+S and 3PMSF, which indicate a tyre's suitability for mud, snow, and severe winter conditions. Let us now start with the first topic, diameter and width. Let us begin by understanding the first two numbers in this tyre marking. In the example tyre, it shows 37 by 12.50. The first number, 37, represents the tyre's approximate overall diameter in inches. This means the tyre measures about 37 inches from the bottom of the tread to the top when properly mounted and inflated. The second number, 12.50, represents the tyre's approximate width in inches measured across the widest part of the tyre. These two dimensions are important because the diameter influences ground clearance, rolling radius, gearing, and obstacle climbing ability, while the width affects the contact patch, flotation, vehicle packaging, and stability. So this is approximately a 37-inch diameter, 12.50-inch wide tyre. Let us understand the two common systems used to describe tyre sizes, flotation nomenclature and metric nomenclature. On the left, the flotation tyre is marked 37 by 12.50 R17. The first number, 37, indicates the tyre's approximate overall diameter in inches. This means the tyre measures about 37 inches from the ground to the top of the tread. The second number, 12.50, indicates the tyre's approximate section width in inches. On the right, the metric tyre is marked 185/75 R14. The first number, 185, indicates the tyre's section width in millimeters. The second number, 75, is the aspect ratio and not a direct measurement. It means the sidewall height is 75% of the tyre's 185mm width. The key difference is that flotation nomenclature starts with overall diameter in inches, while metric nomenclature starts with tyre width in millimeters. Understanding this difference helps engineers correctly compare tyre dimensions and select a suitable tyre for the vehicle. We have now completed our discussion on tyre diameter and width and understood how these dimensions affect tyre size and vehicle performance. Next, let us move to tyre construction and types, where we will understand radial, bias ply, tubed, tubeless, and other commonly used tyre designs. Next in the tyre marking, we see the letter R. This identifies the tyre's construction type. The letter R stands for radial construction. In a radial tyre, the internal body cords run from bead to bead at approximately 90 degrees to the direction of travel, while reinforcing belts are placed beneath the tread. Radial tyres generally provide better ride comfort, lower rolling resistance, improved heat dissipation, and longer tread life compared with traditional bias ply tyres. So, in the marking 37 X 12.50 R17, the letter R tells us that this is a radial construction tyre. This image explains the three common tyre construction codes found in sidewall markings. The letter R means radial construction, where the body cords run from bead to bead at approximately 90 degrees, with reinforcing belts beneath the tread. This is the most common modern design. The letter D, or sometimes a dash, indicates diagonal or bias ply construction, where the plies cross each other at an angle, producing strong sidewalls. The letter B represents belted bias construction, which combines a bias ply carcass with stabilizing belts beneath the tread. These codes help engineers quickly identify the tyre's internal structure and expected performance. Next in the marking, we see the number 17. This represents the rim diameter, measured in inches. It means that the tyre is designed to fit a wheel rim with a diameter of exactly 17 inches. It is important to remember that rim diameter is not the overall tyre diameter. The overall tyre diameter in this example is approximately 37 inches, while 17 inches refers only to the wheel on which the tyre is mounted. Correct rim diameter ensures proper bead seating, safe fitment, and compatibility between the tyre and wheel. Now that we have the overall diameter, tyre width, and rim diameter, several other useful tyre dimensions can be derived. For the example 37 x 12.50 R17, the sidewall height is calculated by subtracting the 17-inch rim diameter from the 37-inch overall diameter and dividing by 2. This gives approximately 10 inches. The aspect ratio is then calculated by dividing the sidewall height by the tyre width, giving approximately 80%. The nominal tyre radius is half the overall diameter, or 18.5 inches. Using the diameter, we can also estimate the tyre circumference at around 2.95 meters. To calculate tyre circumference, simply multiply the tyre's overall diameter by pi. Circumference equals pi times diameter. Finally, this circumference gives approximately 339 tyre revolutions per kilometre, which is useful for speed, gearing, motor RPM, and distance calculations. Next in the marking, we see the letters LT. LT stands for light truck and identifies the tyre's service type. It indicates that the tyre is designed for vehicles that may carry heavier loads, operate at higher inflation pressures, or work under more demanding conditions than standard passenger vehicles. LT tyres generally have a stronger carcass and reinforced construction, making them suitable for pickup trucks, utility vehicles, off-road platforms, and many vehicle applications. However, the LT marking alone does not define the exact load capacity. Engineers must also check the tyre's load index, load range, and recommended inflation pressure. This table explains the common tyre service type codes used on tyre sidewalls and what kind of vehicle each code is meant for. The code P stands for passenger, used for normal passenger cars and small SUVs. LT means light truck and is commonly used for pickups, utility vehicles, off-road vehicles, and heavier-duty applications. ST stands for special trailer, meant only for trailers and towed equipment, not for powered drive axles. T means temporary spare, designed for short distance, limited speed, emergency use. We also see C for commercial, used on light commercial vans and delivery vehicles, and MC for motorcycle applications. The key point is that service type helps match the tyre to the vehicle's duty, load requirement, and operating condition. We have now completed tyre construction and types, including radial, bias ply, tubed, tubeless, and other tyre designs. Next, let us look at load index and speed rating, which define how much weight a tyre can safely carry and its maximum approved operating speed. Next, let us understand the load index. The load index is a numerical code that indicates the maximum weight a tyre can safely carry under specified operating conditions. In our example, the number 124 is the load index. A load index of 124 corresponds to a maximum load capacity of approximately 1,600 kilograms per tyre. However, engineers should not select a tyre based only on this maximum value. Vehicle load distribution, dynamic loads, terrain, and a safety margin must also be considered. So the load index helps confirm whether the tyre can safely support the required wheel load. This image shows how a tyre's load index corresponds to its maximum load carrying capacity. The load index is not the weight itself. It is a numerical code that must be matched with a standard reference table. As the load index increases, the permitted load per tyre also increases. For example, a load index of 100 represents approximately 800 kilograms, while 120 represents about 1,400 kilograms per tyre. In our example, the load index is 124. From the table, this corresponds to a maximum rated capacity of approximately 1,600 kilograms, or 3,527 pounds per tyre. Engineers must still consider inflation pressure, vehicle load distribution, dynamic loading, operating speed, terrain, and safety margin before final tyre selection. This image explains a practical method to estimate the required tyre load capacity and then identify the minimum suitable load index. We begin with the maximum static load on the most heavily loaded wheel. This value is multiplied by correction factors for dynamic loading, terrain severity, operating speed, and the required safety margin. In this example, the static wheel load is 800 kilograms. The dynamic factor is 1.50, the terrain factor is 1.10. The speed factor is 1.05. And the safety factor is 1.15. We will learn how to calculate these factors in the next video. For now, just understand that these factors are to be considered for load index calculation. Multiplying these values gives a required capacity of approximately 1,594 kilograms per tyre. We then compare this result with the standard load index table. Load index 123, rated for 1,550 kilograms, is insufficient. Load index 124, rated for 1,600 kilograms, is the first value that meets the calculated requirement. Therefore, the minimum recommended load index is 124. Next, let us understand the speed rating. The speed rating is a letter code that indicates the maximum speed at which a tyre can safely operate while carrying its rated load under specified conditions. In our example, the letter Q is the speed rating. A Q rating corresponds to a maximum rated speed of approximately 160 km per hour. This does not mean the vehicle should continuously operate at that speed. Engineers must also consider load, terrain, duration of operation, and a factor of safety. For an unmanned ground vehicle, the speed rating should comfortably exceed the vehicle's maximum design speed. This image explains how tyre speed ratings use letter codes to represent the maximum approved operating speed of a tyre under specified load and inflation conditions. As we move through the table, the permitted speed generally increases. For example, N represents about 140 km per hour, P represents 150, and Q represents 160 km per hour. Higher ratings such as S, T, and H correspond to progressively greater speeds. In our example, the final letter, Q, is the speed rating. This means the tyre is rated for speeds up to approximately 160 km per hour under its specified test conditions. Engineers should ensure the selected rating exceeds the vehicle's maximum design speed while also considering load, terrain, operating duration, and a margin of safety. This image shows a practical method for estimating the minimum tyre speed rating required for a vehicle. We begin with the vehicle's maximum intended speed and multiply it by adjustment factors for load, terrain, duration of operation, and safety. In this example, the maximum vehicle speed is 120 km per hour. We then apply a load factor of 1.10, a terrain factor of 1.05, a duration factor of 1.05, and a safety factor of 1.10. Multiplying these values gives a required tyre speed capability of approximately 160 km per hour. Next, we compare this requirement with the standard speed rating table. A P-rated tyre is suitable up to 150 km per hour, so it is not sufficient. A Q-rated tyre is rated for 160 km per hour and therefore becomes the minimum acceptable selection. An R-rated tyre rated for 170 km per hour would also be acceptable. Next, let us understand load range, another important marking found on many light truck, utility, and off-road tyres. Load range is a letter-based classification that indicates the tyre's structural strength and the level of inflation pressure and load it is designed to support. Common examples include load range C, D, E, and F. In our example, the tyre is marked load range E. This is commonly associated with a stronger light truck tyre construction and is often referred to as a 10-ply rating. However, this does not necessarily mean the tyre physically contains 10 plies. It is a strength equivalence classification based on older tyre terminology. As load range increases, the tyre can generally operate at higher inflation pressures and support greater loads, but the exact capacity must still be checked using the manufacturer's load and inflation table. Engineers should therefore consider load range together with the load index, tyre pressure, wheel rating, speed, terrain, and required ride characteristics before final selection. This image compares the most common tyre load ranges from B through H and shows how they relate to tyre strength, ply rating equivalent, and maximum inflation pressure. Load range B represents lighter duty construction with a 4-ply equivalent and a typical maximum cold pressure of around 35 psi. As we move upward through C, D, and E, the tyre becomes progressively stronger and is designed to operate at higher pressures. For example, load range E is commonly associated with a 10-ply rating equivalent, a typical maximum pressure of about 80 psi, and medium to heavy duty applications. Higher classifications such as F, G, and H are intended for heavy, extra heavy, and maximum duty service with greater structural capability and higher pressure ratings. Remember, ply rating is a strength classification, not necessarily the actual number of physical plies. Final selection must still consider the manufacturer's load table, actual inflation pressure, vehicle load, wheel rating, speed, and operating terrain. We have now completed load index and speed rating and understood how they define a tyre's safe load carrying capacity and maximum operating speed. Next, let us look at the DOT code, which helps identify the tyre's manufacturing details, production date, and age. Next, let us introduce the DOT code, which is another important marking found on the tyre sidewall. The DOT code confirms that the tyre has been manufactured and identified according to applicable Department of Transportation requirements. It is made up of a combination of letters and numbers that provides traceability information about the tyre. For engineers, this marking is useful when checking tyre origin, manufacturing details, production records, and tyre age during inspection or selection. In the next section, we will break down the DOT code and understand what each part represents. The DOT code provides important traceability and manufacturing information about a tyre. In this example, the code begins with the letters DOT. This is the certification mark indicating that the tyre meets applicable United States Department of Transportation requirements. The next section, shown here as X1A3, represents identification information with the tyre's manufacturing source. This includes the plant code and may also include additional manufacturer or tyre-specific identification characters. The final 4 digits form the tyre's date code. The first 2 digits indicate the week of manufacture, while the last 2 digits indicate the year. In this example, 15 means the tyre was manufactured during the 15th week of the year. 25 represents the year 2025. For engineers and maintenance teams, the DOT code supports tyre identification, production traceability, age verification, inspection planning, and replacement decisions. This image provides a simple guideline for assessing tyres based on their age. Tyres between 0 and 3 years old are generally considered to be in an excellent age range, provided they are undamaged and properly maintained. From 3 to 5 years, the tyre should be monitored for signs of aging, such as cracking, hardening, deformation, or unusual wear. Between 5 and 7 years, inspections should become more frequent even when sufficient tread remains. For tyres aged 7 to 10 years, engineers should carefully evaluate their condition and operating history to determine whether replacement is necessary. At 10 years or more, replacement is generally recommended because rubber degrades with time. Remember, tyre age is only one factor. Load, terrain, damage, and manufacturer guidance must also be considered. Let's have one last look at the agenda. We have now completed the DOT code and understood how it helps identify a tyre's manufacturing details and production date. Next, let us look at specialized markings, particularly M+S and 3PMSF, which indicate a tyre's suitability for mud, snow, and severe winter conditions. This image explains the M+S marking commonly found on all-terrain and off-road tyres. M+S stands for mud and snow. It indicates that the tyre's tread pattern has been designed to provide better traction than a standard road tyre in loose conditions such as mud, light snow, gravel, and soft terrain. This improved performance usually comes from wider tread grooves, larger tread blocks, and more open spaces that help the tyre clear mud and snow from the tread. However, an M+S marking is primarily a manufacturer's classification based on tread design. It does not necessarily mean the tyre has passed a certified severe winter performance test. Therefore, engineers should not treat M+S as proof of full winter capability. Tyre selection must still consider terrain, temperature, load, pressure, and operational requirements. For more demanding winter conditions, look for additional certified markings such as the Three Peak Mountain Snowflake or 3PMSF symbol. The 3PMSF marking stands for Three Peak Mountain Snowflake. It is identified by a snowflake symbol placed inside a mountain with 3 peaks. Unlike the M+S marking, 3PMSF is not based only on tread appearance. It indicates that the tyre has met a defined performance standard for acceleration traction in severe snow conditions. This means a 3PMSF-rated tyre has demonstrated better snow performance than a standard reference tyre during controlled testing. However, the marking should not be misunderstood as a guarantee of maximum grip in every winter situation. It does not automatically confirm equal performance on ice, deep snow, wet roads, or during braking and cornering. Engineers should therefore consider 3PMSF together with tread design, rubber compound, load rating, inflation pressure, temperature range, terrain, and vehicle requirements. In simple terms, M+S is mainly a tread classification, while 3PMSF represents tested severe snow capability. This image compares 3 tyre categories: a standard highway tyre, an M+S tyre, and a 3PMSF tyre. The highway tyre is designed mainly for paved roads. Its shallower grooves and continuous ribs provide quieter operation, lower rolling resistance, and longer tread life on hard surfaces. The M+S tyre is intended for mud and light snow. It uses deeper grooves, wider tread openings, and larger tread blocks to improve traction and help clear loose material such as mud, gravel, and snow. The 3PMSF tyre is designed for more severe winter conditions. Its deeper tread and additional sipes create more biting edges for traction in snow and ice. Unlike M+S, the 3PMSF symbol indicates that the tyre has met a defined severe snow performance test. In summary, use highway tyres for paved road efficiency, M+S tyres for mixed terrain and light snow, and 3PMSF tyres when tested severe snow capability is required. This brings us to the end of Part 2, Tyre Markings. In this video, we understood how tyre diameter and width are identified, how construction types such as radial and bias ply are marked, and how load index and speed rating define the tyre's operating limits. We also looked at the DOT code, which helps identify the tyre's manufacturing details and age, along with specialized markings related to direction of rotation, tubeless construction, load range, and other operating requirements. Thank you for attending this session. We hope you found the video informative and useful. In the next part, we will continue building our understanding of tyre selection and vehicle performance.